Hello.
Our next speaker is Shantanu from HRI. So he's talking about irreducible module loop derivation of rational quantum. Welcome, Shantanu. Share the presentation.
Okay, sir. Can I start, sir?
Yes.
Okay. So first of all, I'd like to thank the organizer of this conference for giving me this opportunity to present my paper. And the title of the talk is Irreducible Model for Loop of Derivations of Rational Quantum Torus. And the content is this. So first we'll give some basic introduction and history about rational quantum torus. Then we'll construct a loop of quantum torus, and then we'll state our main theorem, and later we'll try to sketch the proof of the theorem. Okay. So one of the main problem in representation theory is classification of different kind of irreducible modules for infinite dimensional Lie algebras. In this talk, we will consider loop of derivations of rational quantum torus and partially classify its irreducible Z-graded weight modules. Assume A be the Laura polynomial ring in commuting variables, and derive with the space of all derivations of A. In 1986, Sen and in 1996, Rao independently gave several irreducible representation of Dere, and later in 1992, Larson constructed a large class of modules for Dere, and these modules are called as modules of tensor fields. And later in 2003, Jiang and Ming proved that in order to classify irreducible integrable modules for the full toroidal Lie algebra, it is enough to classify irreducible Z-graded weight modules for Dere semidirect A. And in 2004, Rao has given a classification of irreducible modules for Dere semidirect A with finite dimensional weight spaces, and where the action of A is associative. In fact, he proved that for n greater than or equal to 2, modules of tensor fields for Dere exhausts all Z-graded irreducible weight modules of Dere semidirect A with finite dimensional weight spaces. Later in 2016, Billig and Futerni completely classified irreducible modules with finite dimensional weight spaces for Dere. Now, suppose CQ be the non-commutative Laura polynomial ring associated to a rational quantum matrix Q, and der CQ be the space of all derivations of CQ. In 2014, Rao, Bhatta, and Sharma considered the Lie algebra der CQ semidirect CQ, and they partially classified Z-graded irreducible weight module for this Lie algebra, and for n greater than or equal to 2, they showed that this type of modules are of the form V tensor with CQ, where V is a finite dimensional GLN module. In 2016, Zhenqiang Liu and Keiming Zhao completely classified irreducible bounded weight modules over der CQ. Recently in 2022, Chakraborty and Rao considered loop of Dere semidirect A and classify all irreducible Z-graded weight modules when the action of A tensor B on the modules is associative. Now we ask the similar question for rational quantum case. So in a recent work, we considered the loop of der CQ semidirect CQ and classify its irreducible Z-graded weight modules when CQ1 tensor B acts associatively and CQ2 tensor B acts anti-associatively. Later we will define what is CQ1 and what is CQ2 is. So a matrix Q is called a rational quantum matrix if all its diagonal elements are 1 and its ij entry is its jith entry is inverse and each ijth entry is a root of unity. Such matrices are called rational quantum matrix. And assume CQ be the Laura polynomial ring in non-commutative variables T1 up to Tn with the conditions Tij is Qij times Tj. Then for any A in Zn, suppose T power A is Q1 power An up T2 power A2 up to Tn power An, then we can see that CQ is a Z-graded non-commutative associative algebra over C. Hence, it will be an Lie algebra over C. Now, in order to look at the Lie brackets of CQ clearly, one define two functions, sigma and f from Zn cross Zn to C star, by the following. So sigma of AB is just product of Qji power aj times bi, where I and j run from 1 to n with the condition I less equal to j, and f of AB is sigma AB times sigma BA inverse. Then we can check that leave bracket of t power a comma t power b is just equal to sigma AB minus sigma BA times t power a plus b. Now we define a subgroup of Zn. So radical of f is set of all points a in Zn such that f of AB is 1 for every point b in Zn. That means radical of f will contain set of all a in Zn such that sigma AB is sigma BA from this f of AB equal to sigma AB times sigma BA inverse. Okay, and this will become a subgroup of Zn. Now we state a theorem of Berman and his co-authors. It says that the center of CQ has a basis consisting of monomials t power a, where a is in radical f, and the commutator of CQ, that means leave bracket CQ has a basis consisting of monomials t power a, where a is outside radical f. And as a Lie algebra, we can write CQ as direct sum of commutator of CQ and center of CQ. And now suppose del CQ with the space of all derivations of CQ, and one can check that del CQ is Zn graded as Lie algebra, and assume del CQ of A be the eighth component of del CQ. Then in the same paper, they prove that eighth component of del CQ is equal to C times adjoint of t power A if A is outside radical f, and it is equal to C linear span of t power A del I if A is in radical f. Okay. Now for any U in Cn and R in radical f, we define DUR is equal to sub over I equal to 1 to n UI t power R del I. Then we have the following leave bracket. So leave bracket at t power s comma at t power R will be just sigma SR minus sigma RS times at t power s plus R, and leave bracket DUR comma at t power s will be just inner product US sigma RS at t power R plus s, and leave bracket DUR comma DU prime R prime is DW R plus R prime, where W is just sigma R prime inner product UR prime minus U prime R. In particular, if we take CQ symmetric del CQ, this will become a Lie algebra with the natural action of del CQ on CQ, and the action is just at t power s action on t power R is just sigma SR minus sigma RS times t power s plus R, and DUR action on t power s is just inner product US sigma RS t power R plus s. So using these actions, we can see that CQ symmetric del CQ will become a Lie algebra. Now suppose B is any commutative associative unital algebra over C, and then one can consider the loop algebra tau B is just tau tensored with B with the leave brackets. So leave bracket x1 x tensor B1 comma y tensor B2 is just leave bracket x comma y tensor B1 B2, and one can check that tau is isomorphic to tau tensor 1. Tau is the Lie algebra, this one CQ symmetric del CQ. Now take H be the complex span of DU0, where U is in Cn, direct sum C times t power 0. Then H is a maximal abelian subalgebra of tau. Now consider two subalgebras. CQ1 is just this CQ, and CQ2 is span of at t power R minus t power R, where R is in Zn. Then we can check that CQ2 is isomorphic to CQ1 as Lie algebra, and the isomorphism is just at t power R minus t power R goes to t power R. Now a module V of tau is called weight module if V is diagonalizable with respect to H. That means V can be written as direct sum of lambda in dual of H V lambda, where V lambda is set of all points of V such that H action on V is lambda H times V for all H in H, and elements of the set of all lambda in H star such that V lambda non-zero are called weights of V. Now it is easy to see that for any indecomposable weight module V is Zn graded. We are going to construct a Zn graded module for tau V from a Zn graded module of tau. Suppose phi is an algebra homomorphism from B to C such that phi of 1 is 1 and V is an irreducible finite dimensional GLNC module. We define a tau module structure on F alpha V. This is just V tensor with CQ by the following actions. So at t power r action on V tensor t power s is just sigma rs minus sigma sr times V tensor t power r plus s, and du r action on V tensor t power s is just sigma rs inner product u comma s plus alpha plus sum over ij ri uj e ij action at V tensor t power r, V tensor t power r plus s, and t power r action on Vs is just sigma rs times V tensor t power r plus s. So using these actions, we can dividing by this, we can give a tau module structure on F alpha V. Now on F alpha V, we can give a tau V module structure by the action is where the action is x tensor B, action at V is just 5V times x acting at V, and we will denote this type of modules by F alpha V comma phi. In 2014, Rao, Bhatta, and Sharma proved that F alpha V is irreducible module for tau. Therefore, it will be irreducible module for tau V also. And in the same paper, they proved that suppose if you take an irreducible ZN graded tau module V prime with finite dimensional with weight spaces with respect to the maximal abelian subalgebra H, and on the modules CQ1 acts associatively and CQ2 acts anti-associatively and T0 acts as identity, then we can see that V prime should be isomorphic to F alpha V for some alpha in Cn and finite dimensional irreducible GLN module V. So in this work, we kind of generalize this result for tau V. So our main theory is just suppose if you have an irreducible tau V module with finite dimensional weight spaces with respect to the Cartan maximal abelian algebra H, and also assume that CQ1 tensor B acts associatively on the modules and CQ2 tensor B acts anti-associatively on the modules and T0 acts as identity on V, then what we can prove that V is isomorphic to F alpha V psi for some alpha in Cn, and V is a finite dimensional GLNC module, and psi is an algebra homomorphism from B to C. Now we are going to sketch the proof of this theorem. Okay, so suppose V is an irreducible tau V module with finite dimensional weight spaces, and assume the action of CQ1 tensor B is associative and action of CQ2 tensor B is anti-associative, and T0 acts as identity on V. Suppose V is direct sum of R in Z and VR, be its weight space decomposition, where VR is just set of all vector V in V such that du0 action on V is inner product u comma r plus alpha times V for all u in Cn. Now since T0 acts as identity on V, each weight space will be of same dimension. Also, we can see that one tensor B lies in the center of tau. Therefore, it will act scalarly on V. The action of CQ1 tensor B is associative. So, we can find an algebra homomorphism psi from B to C such that action of one tensor B at V is just psi B times V for all V in V. Suppose M is the kernel of this homomorphism, therefore M will be a maximal ideal of B, and we will denote an element X tensor B of tau V by XB, and let U of tau B denote the universal enveloping algebra of tau B, and L of tau B be the two-sided ideal of U of tau B generated by these three elements. So the first type of elements are coming because of CQ1 tensor B acts as associatively, and the second type of elements are coming because CQ2 tensor B acts anti-associatively. This is what that's why sigma SR we are getting, not sigma RS here. And third element is coming because T0 acts as identity. So we just take U of tau B, L of tau B by is the two-sided ideal of U of tau B generated by this type of elements. Then we can see that L of tau B acts trivially on the modules. Therefore, V will be a U of tau B quotient L of tau B module. Now, suppose U1 is that U of tau B quotient L of tau B, that quotient space, and we define the elements T U R B1 B2 by sigma RR T power minus R B1 D U R B2. This is an element of E1, and what we take T is the span of T1 TU or B1 B2, this type of elements, and G is the least algebra generated by T U or B1 B2 and T power minus S B3 and add T power S B4. And I is the subalgebra of G generated by the elements of the form T power minus S B1 add T power S B2. Then using the associative action of CQ1 tensor B, we can prove that I is a abelian ideal of G. And we have the following theorem. So this theorem says that T becomes a Lie algebra and leave bracket dv0 comma T U R B1 B2 is 0 for any V U and V in Cn and R in radical F and B1 B2 in B. And if we have a weight space decomposition of V, that is direct sum of R in Z and VR, then each weight space is T invariant, and we can prove that each weight space is T irreducible. Okay. Now we define a different kind of elements. T prime U R B1 B2. This is just T U R B1 B2 minus D U0 B1 B2, and T prime be the set spanned by T prime be the space spanned by T prime U R B1 B2. Then what we can prove that T prime is a Lie algebra. Now we state a theorem of Humphrey's book. Suppose we have a G algebra, Lie algebra G, and V prime comma rho B its irreducible finite dimensional module. Then rho of G is a reductive Lie algebra whose center is at most one dimensional. Now we have that Lie bracket T comma T is sits inside T prime. Therefore, from this theorem of Humphrey's books and this theorem, the fourth part of this theorem, what we can say that each weight space VR is T prime irreducible. So each weight space will be irreducible module for this T prime, and each weight space are isomorphic. So VR is isomorphic to VS as T prime module. Now we consider a different kind of elements I U R B1 B2, that is just psi of B1 times root over sigma RR DUR tensor B2 minus DU0 tensor B1 B2, and similarly consider the space I is spanned by this type of elements. Then we can also see that I is a Lie subalgebra of tau B, and what we can say that I and T prime are Lie algebra isomorphic. So there is isomorphism between I and T prime. Now we consider the subspace of the module V, that is spanned by root over sigma mm T power m action on V minus V, where V is running from V is inside zeroth component of the weight space. And what we can see that this will be exactly equal to span of root over sigma mm T power m action and at V minus V, where here V is running all over V, capital V. So and we can prove that this subspace is a T prime submodule of V. And if we take the quotient module, that means V quotient W, then that will be so V quotient W will be isomorphic to zeroth component of the weight space as T prime module. Now, using results of Chakraborty and Rao, what we can prove that DU0 tensor B acts as scalar on the zeroth component of the module. And from this, we can prove DUR tensor B on V acts as psi B times DUR. And using the associative and anti-associative action of CQ1 tensor B and CQ2 tensor B respectively, we can prove that action of add T power S tensor B is same as psi B times add T power S. So this implies that X tensor B action on V is same as psi B times X action at V for all X in tau, V in B, and small v in capital V. So from previous discussion, we can prove the following. So it says, suppose we have an irreducible tau b module with finite dimensional weight spaces, and CQ1 tensor B acts associatively on the module, and CQ2 tensor B acts anti-associatively on the modules, and T naught acts as identity on the module. Then it should be an irreducible module for tau. Now we have a theorem of Rao and Bhatta and Sharma. It says that if we have an irreducible Z-graded tau module with respect to H, and assume the action of CQ1 is associative and action of CQ2 is anti-associative, and T naught acts as identity, then V prime should be isomorphic to F alpha V for some alpha in Cn and finite dimensional irreducible GL module in V. So using this theorem and this theorem, we can prove our main result, which says that if we have an irreducible tau b module with finite dimensional weight spaces with respect to H, and where on the module CQ1 tensor B acts associatively and CQ2 tensor B acts anti-associatively, and T naught acts as identity, then V should be isomorphic to F alpha V psi, where alpha is in Cn, V is a finite dimensional irreducible GLNC module, and psi is a algebra homomorphism from B to C. Thank you, sir. It's over.
Is there any questions? So there is no question from the seminar hall. So maybe any question from you with two participants? Seems like there is no question. Thank you, Shantanu, once again.